Recall that periodic law states that when the elements are arranged by atomic number, their physical and chemical properties vary periodically, hence the name periodic table. We'll look at three periodic properties: atomic radius, ionization energy, and electron affinity. Look at atomic radius first. We can't measure the exact size of an isolated atom because its outermost electrons have a chance of being found relatively far from the nucleus. It's kind of an electron cloud around it, not a distinct location around the nucleus. However, we can measure the distance between two atoms' nuclei, which gets us to the definition of a covalent radius. Of an atom, this is 1/2 the distance between the nuclei of two like atoms joined in a molecule. Ionic radius is the same thing. It's talking about the distance between two nuclei, taking half the distance to be that radius as well. Within each period, a horizontal row, the atomic radius tends to increase with decrease in atomic number, from right to left. Within each group, a vertical column, the atomic radius tends to increase with the period number, top to bottom. So basically, your largest radii will be down to the lower bottom of the periodic table, the lower left bottom of the periodic table. Two factors determine the size of an atom. First, why does it increase down? Well, as we go down the periodic table, the valence shell gets larger. We are adding more shells as we go down the table, making the outer electrons further from the nucleus, with less attraction for the nucleus, therefore it spreads out more. Why does it decrease across? The effective nuclear charge, which is the positive charge an electron experiences from the nucleus, minus any shielding effects from intervening electrons, gets larger as we go across the periodic table. As the effective nuclear charge increases, valence electrons will be pulled toward the nucleus more and held more tightly, making the atom smaller. Here's some representation of the different atomic radii. And you notice that it's larger here at the bottom left corner. Let's arrange the following in the order of increase in atomic radius. You have calcium, nitrogen, arsenic, fluorine, and barium. One thing to realize when you're answering a question like this is, what does it mean by increase in atomic radius? That means from the smallest atomic radius to the largest atomic radius. Remember the trim. Atomic size period increases across from right to left and top to bottom. Locating the atoms on the periodic table, find the following. Basically, since barium is at the bottom here, that's going to be our largest size. Next in line from that would be calcium. Calcium would be larger than arsenic. Arsenic would be larger than nitrogen. And nitrogen will be larger than fluorine, fluorine being the smallest. Cations are smaller than neutral atoms, so sodium plus is smaller than sodium. Sodium has a 3s1, so basically when it goes to be a cation, it's going to lose that outer shell, that 3s1, so therefore it's smaller. Cations also have more protons than they have electrons, therefore the electrons are going to be pulled more toward the nucleus, also making it smaller. Anions are larger than their neutral atoms, so chlorine minus is larger than chlorine. An anion has more electrons than protons. Therefore, the electrons are pulling out more outward from the nucleus, making it larger. There is more electron-electron repulsion, and a smaller effective nuclear charge, causing the anion to get larger. Within an isoelectronic group of ions, the one with the greatest nuclear charge, largest excess of protons, will be the smallest. So if we look at argon, Cl minus, calcium 2 plus, sulfur 2 minus, and potassium plus, they all have 18 electrons. They're all the same electron configuration, but they all have different number of protons. For isoelectronic groups, the larger the positive charge, the higher the effective nuclear charge, the more pull the valence electrons will have by the nucleus, the smaller the species. So if we look at the atomic number, which gives us the number of protons, the species with the largest number of protons, when we compare isoelectronic groups, those species that have the same number of electrons, will have the most pull on those outer electrons, therefore be the smallest. So looking at this set of species, we see that calcium has the largest number of protons. Therefore, calcium will be the smallest in this group. Next in size would be potassium plus, followed by argon, followed by chlorine, followed by sulfur 2 minus, sulfide ion, which will be the largest. Ionization energy. The first ionization energy of an atom is the minimum energy needed to remove the highest energy outermost electron from the neutral atom in its gaseous state. For the lithium atom, the first ionization energy is illustrated by the following. You got lithium going to lithium plus 1 electron. The ionization energy to pull off that electron is approximately 520 kilojoules per mole. Metals tend to give up valence electrons while nonmetals tend to gain electrons. So the energy must be absorbed, meaning the endothermic process, to remove electrons. Therefore, we have positive ionization energies. There is a general trend that ionization energies increase across a period, horizontal row. This trend is the opposite of the atomic radius because it is more difficult to remove an electron that is closer to the nucleus in a smaller atom. So it's the complete opposite trend of the atomic radius. The smaller the species, the higher the ionization energy because it's harder to pull off the electrons. The larger the species, the easier it is, the smaller the ionization energy. The trend for ionization energy increases up the group, meaning your vertical column. Summary: ionization energies increase towards the top of the right corner of the periodic table, with helium having the highest ionization energy. Basically, the larger the radius, the smaller the ionization energy. Note, there are some exceptions to the trend, such as between group 2A and 3A and 5A and 6A. The electrons of an atom can be removed successively. The energies required at each step are known as first ionization and second ionization energy, and so forth. The second ionization tends to be larger than the first ionization because now you're dealing with ions, charged species, which makes it even harder to pull off an electron from a charged ion than a neutral species. Therefore, more energy will be required. Look at lithium plus going to 2 plus. The second ionization energy is 7,298 kilojoules per mole. That is extremely larger than the first ionization energy. You got to realize once we took off 1 electron from lithium, it got to an octet, so it really doesn't want to lose any more electrons. So pulling that second one is going to be even harder because it's a charged species as well as you're trying to pull it off from its octet. Range the following in order of increase in first ionization energy: arsenic, calcium, oxygen, and nitrogen. Realize once again we're going from smallest ionization energy to largest ionization energy. Periodic trends pointing up and going to the right. Let's locate our atoms on the periodic table. So looking at this, we know that oxygen is going to be the largest ionization energy. It will be bigger than nitrogen. Nitrogen will be bigger than arsenic. and then arsenic would be larger than calcium, with calcium being the smallest ionization energy. Electron affinity. Electron affinity is the energy change for the process of adding an electron to a neutral atom in a gaseous state to form a negative ion. This is the opposite of ionization energy. Electron's affinity process releases energy. It's an exothermic process instead of an endothermic process that was the case for ionization. Therefore, it tends to be a negative value. Look at chlorine. Taking on an electron, forms Cl-. Electron affinity is a negative 349 kilojoules per mole. The more negative the electron affinity, the more stable the negative ion that is formed. Broadly speaking, the general trend goes from lower left to upper right as electron affinities become more negative. So although we have the same trend as ionization energy up and to the right, you got to realize it's an increasing in negative value. It's not a positive value, so it's increasing in negative value, so it's kind of the opposite of ionization energy. Same trend, different numeric number based on the sign. Homework 63.